The question is, how often does it happen, and how widely spaced are the civilizations?
The concept of what existed before the Big Bang has long captivated scientists and the general public. Brian Cox, a renowned scientist, has proposed theories that have both educated and terrified us about the universe's origins. But what existed before the cosmos began? Can inflation and the nature of nothingness address this question? In this essay, we'll look deeper into these exciting scientific questions. Essentially, what happened before the Big Bang, right? You have to be careful with the language, so if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it as we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. What existed before the Big Bang? This question has always been a challenge for scientists, but now it seems they found the answer to it. It has left scientists shocked as Brian Cox revealed that something terrifying existed before the Big Bang. So the idea is the universe was there, in a sense, cold and empty, and expanded extremely fast. That expansion slowed down and stopped, and the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which were made. That's what we call the Big Bang. The Big Bang is a popular scientific theory describing the beginning of the universe. According to this theory, the universe began as an incredibly small, hot, and dense singularity about 13.8 billion years ago. From this state, the universe expanded rapidly, undergoing a period of cosmic inflation. This process led to the formation of elementary particles, atoms, and eventually galaxies, stars, and planets. The Big Bang explains the distribution of galaxies and the cosmic microwave background radiation, a trace of the initial expansion. That theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever, and it just stops in little patches. So, you imagine this: the fabric of the universe, space-time, stretches, and then it slows down and stops in little patches. Each one of those patches is basically a Big Bang and a universe of which ours is one. So, you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs, and that's called the inflationary multiverse. Eternal inflation theory is a concept in cosmology derived from the inflationary model of the early universe. Cosmic inflation is a period of rapid expansion of space-time immediately following the Big Bang. Eternal inflation theory extends this idea, suggesting that inflation does not occur once, but can continue forever in certain regions of space. According to this theory, in each region of space, inflation can end and create a pocket universe, while other regions continue to experience inflation. This leads to a multiverse structure, where an infinite number of pocket universes exist in parallel, each of which may have different physical laws and fundamental constants. Eternal inflation is seen as an explanation for a number of problems in modern cosmology, including the homogeneity and flatness of the observable universe. It also helps explain why the universe came into being as an independent event, without any special initial conditions. However, the theory of eternal inflation has also faced many controversies and challenges. Some scientists criticize it as untestable, and therefore not strictly within the realm of empirical science. They argue that without a way to test these daughter universes, the theory cannot be confirmed or disproved. Despite its controversy, the theory of eternal inflation remains an important part of modern cosmology, helping to expand our understanding of the structure and formation of the universe. In the vast expanse of the cosmos, the concept of absolute nothingness appears more theoretical than real. Even if all energy were to be stripped from the universe, it would still not be truly empty. Our universe is brimming with matter, radiation, antimatter, neutrinos, dark matter, and dark energy. Even in the absence of energy, the universe continues to generate new forms of it, perplexing our understanding. It seems the universe does not conform to our notion of complete emptiness. If we were to remove all energy, creating a void, one might expect the universe to reach an absolute zero state, devoid of particles. Yet, this is not the case. Even in an ostensibly empty universe, expansion still generates radiation. This phenomenon reaches far into the future and back to the time before the hot Big Bang, indicating that the universe never truly becomes void. Given this perpetual presence, is it plausible that the universe originated from nothing? It seems that something always persists. Even if particles, antiparticles, photons, and quanta were removed, empty space remains. If we distance ourselves from any sources of mass or energy, clear the space of external electric, magnetic, and gravitational fields, and prevent photons or gravitational waves from entering, a form of physical emptiness still exists. Quantum fields persist, as do the fundamental constants and laws of physics. Within that space, there remains an intrinsic, finite, positive and non-zero value of zero-point energy, suggesting that the universe is never truly devoid of substance. The nature of nothingness in science is a complex and controversial topic, involving fields such as cosmology, quantum physics, and scientific cleanness. Nothingness, in the conventional sense, is a state where nothing exists. No matter, no energy, no time, and no space. However, scientists have discovered that the concept is not quite so simple. In cosmology, nothingness is often considered to be the state before the present universe began to exist. According to the Big Bang theory, the universe began at a singularity of infinite heat and temperature and expanded from there. But the question of what happened before the Big Bang and whether there was a state of absolute nothingness before that is still not a mystery. Some theories, such as the equestrian universe and multiverse models, suggest that our universe may be just one of an infinite number of universes created from a sea of space, a postulate that exists forever. In matter, the concept of void is viewed differently. According to the Heisenberg-defying principle, there is no truly empty space, but rather it is always filled with all sorts of virtual vibrations and particles. These fluctuations are constantly appearing and disappearing, creating energy and matter from what we perceive as nothingness. This phenomenon is called vacuum fluctuations, and it suggests that even in the emptiest of states, there is still quantum physics at work. A prominent example of nothingness creating matter is Hawking radiation, whereby black holes can emit radiation that acts as quantum effects in the vacuum near their borders. This shows that the empty space around the error is not really empty, but filled with pairs of particles and counterparticles. Thus, in science, nothingness is not a static state where nothing happens. Instead, it is a background full of states and energy. This opens up profound questions about the nature of reality and existence, forcing us to rethink what we understand about the universe and existence itself. Nothingness in science is not just a conceptual thing, but also a vibrant and exploratory field of study. This represents the closest approximation to nothing within our universe. While you might envision an even more nothing-like state, it lacks physical reality. No experiment can replicate such a condition. By adhering to scientific principles, we acknowledge that something always exists because true nothingness cannot coexist in our universe. Yet the question of why remains unanswered by science. Presently, our universe appears far from empty. It's teeming with stars, gas, dust, galaxies, quasars, cosmic rays, and radiation from both starlight and the remnants of the Big Bang. With improved observational tools, we could potentially detect additional signals that we anticipate are present. This encompasses gravitational waves generated by any mass moving through a changing gravitational field, the mysterious signals from the constituents of dark matter, and a broader perspective on black holes, both active and dormant. Aside from the most radiant objects, everything in our universe is in constant flux. From a physical standpoint, understanding this grand-scale evolution is fascinating. The fabric of our universe, space-time, is expanding. This means that the distance between any 2 points, the time light takes to travel between them, and the light's wavelength all increase over time. Consequently, as the universe expands, it also cools. Light stretches to longer wavelengths, transitioning to lower energies and cooler temperatures. Our universe, once hotter, continues to cool as it ages. During this process, mass and energy attract each other, forming clusters and an extensive cosmic network. If we removed all matter, radiation, and energy, what remains is empty space, still expanding and governed by the laws of physics and quantum fields. This represents the closest approximation to true nothingness while adhering to physical principles. For physicists, removing more would create an unrealistic state, unreflective of our cosmos. Dark energy would still be present in this hypothetical universe devoid of matter. At the lowest energy state of every quantum field, we reach the zero-point energy of space, where no additional energy can be extracted for mechanical work. Quantum fields are the foundation of modern physics, describing how elementary particles interact and create matter. According to quantum theory, space is not empty, but filled with quantum fluctuations and virtual particles. These particles can appear and disappear in a split second. This process, called vacuum fluctuations, leads to the creation of real particles, which contribute to the formation of matter. This explains how elementary particles interact to create atoms and molecules, the basic structures of all matter in the universe. In a universe containing dark energy, a cosmological constant, or the zero-point energy of quantum fields, it's plausible that the zero-point energy wouldn't be truly zero. As the universe continues to expand and cool, there will come a time in the distant future when radiation becomes the dominant component, surpassing other forms of matter and radiation, leaving dark energy as the primary influence. However, there's also a period in the universe's history, not in the future, but in the distant past, when something else besides matter and radiation held dominance. During cosmic inflation, prior to the hot Big Bang, our universe underwent extremely rapid and constant expansion. Instead of being dominated by matter and radiation, the cosmos was controlled by the field energy of inflation, akin to today's dark energy, but much more potent and expanding at a significantly faster pace. What if the universe has a definitive beginning despite the theory of eternal inflation? To explore this, we must differentiate 3 interconnected concepts: the hot Big Bang in our universe, cosmic inflation's role in setting up the Big Bang, and the quest for the ultimate origin of our universe. In the early 20th century, 4 pivotal discoveries converged. Friedman's application of Einstein's relativity to a dynamic universe, revealing expansion or contraction based on energy density, and Leavitt's period luminosity relation for variable stars, linking their brightness cycles to inherent luminosity. Observations by Vesto Slipher measuring the shift in light, either red-shifted or blue-shifted, from our solar system's perspective in spiral and elliptical nebulae, which were later identified as galaxies, indicated that these galaxies were moving away from us at incredibly high speeds. Edwin Hubble, alongside Milton Humason, identified similar types of variable stars to those identified by Henrietta Leavitt in spiral and elliptical nebulae. This enabled them to gauge the distances to these galaxies and confirmed they were beyond our own. These findings, combined with other data, led to the concept of the universe expanding. If the universe expands, it suggests that over time, space itself stretches, causing the matter within it to become less dense. As space expands, radiation, like light waves, not only becomes less concentrated but also stretches, leading to the universe cooling. If we rewind the clock, the opposite would occur to matter and radiation in the universe. In earlier times, when the universe was younger, it was denser and hotter. If we rewind further, all matter and radiation would have been squeezed into a smaller space, increasing the density of the universe. The light, which stretched due to cosmic expansion when we reverse time, would have had a shorter wavelength, resulting in hotter temperatures. If you envision going back as far as physics permits, you'd reach a singular state where all matter and radiation existed within a single point of infinite density and temperature. The initial idea of the Big Bang theory resulted in the formation of 5 key expectations regarding the early universe's hot and dense conditions. These forecasts became the foundation of the Big Bang theory. The universe ought to demonstrate expansion as indicated by a distinct redshift distance relationship among extragalactic objects. Initially, the universe should have been relatively uniform, with structures like stars, galaxies, and clusters of galaxies gradually forming and evolving over time. In the past, the universe was hotter, preventing the formation of stable neutral atoms. This prediction led to the discovery of the cosmic microwave background, which is observable today. In the initial stages of the universe, when it was extremely hot, atomic nuclei couldn't form stably. This led to the creation of light elements such as hydrogen, helium, lithium, and their isotopes. The universe was so hot that neutrinos played a significant role. Recently, this prediction was confirmed, indicating that cosmic neutrinos should have detectable effects on both the large-scale structure and the leftover radiation from the Big Bang, with strong observational evidence supporting these predictions. The Big Bang theory has remained uncontested as the primary explanation for the early universe since the mid-1960s, coinciding with the discovery of the cosmic microwave background. As evidence supporting the hot Big Bang theory grew in the 1960s and 1970s, certain challenges surfaced that the Big Bang alone couldn't resolve. Several observations contradicted the concept of the universe originating from a singular state of incredibly high temperatures and densities. 3 of these challenges stand out. Firstly, there's the horizon problem. When we observe different directions, the universe seems to possess uniform temperatures and density throughout. However, since the onset of the hot Big Bang, these regions have never had the opportunity to communicate, exchange information, or achieve thermal equilibrium with one another. This raises the question, how did they evolve to exhibit uniform temperature and conditions across the board? Next, let's consider the issue of flatness. In a universe that's expanding, there's a continual tug-of-war between the initial expansion pushing things apart and gravitational forces attempting to pull everything back together. Remarkably, in our universe, these opposing forces appear to be perfectly balanced, resulting in a spatially flat universe. The question arises, why did our universe come into existence with these particular characteristics? Moving on, we encounter the monopole or ancient relic dilemma. If the universe underwent extreme temperatures and energy conditions in its early stages, why do we not observe any exotic remnants such as right-handed neutrinos and magnetic monopoles? Theoretically, these particles should be detectable and still present today. Rather than just taking these conditions as how the universe came to be, which contradicts the scientific method, scientists are looking for a mechanism that would establish and arrange these initial conditions. Alan Guth introduced a solution to these cosmological mysteries in 1980 with a groundbreaking paper. He suggested that an early phase of rapid and continuous expansion, where the universe's energy wasn't spread among matter and radiation particles but was an intrinsic part of space itself via a field or another mechanism, could solve all 3 issues. Regarding the horizon problem, the uniformity of temperature and density throughout the universe is attributed to the past interconnectedness of everything. This connection, stretched during the early expansion phase, is called inflation, resulting in the current conditions observed. For the flatness problem, inflation expanded the universe so much that regardless of its initial state, the visible part now appears uniformly flat. As for the monopole problem, the absence of ancient remnants is explained by inflation, preventing the universe from reaching excessively high energies or temperatures. The maximum temperature reached after inflation avoids the formation of these remnants. Inflation not only explains these phenomena, but also presents a compelling alternative to the standard hot Big Bang model. Additionally, a further issue was addressed. To demonstrate how a uniform and isotropic early universe could be reinstated after inflation. It became evident that inflation could act as a quantum mechanism for seeding the universe with initial imperfections or the origins of cosmic structure, ultimately leading to the intricate formations we see today. In the 1980s, inflation theory made precise and testable forecasts about the beginnings of cosmic structure that should be detectable in both the cosmic microwave background and the large-scale layout of the universe. These forecasts, crafted decades ago, have been validated by observations spanning from the 1990s to the present day, encompassing an almost, though not entirely, scale-invariant spectrum of imperfections, variations in density and temperature, density irregularities that are entirely adiabatic and not at all isocurvature in essence, fluctuations on scales larger than what a signal traveling at the speed of light in an expanding universe could generate, and a maximum temperature limit for the universe during the hot Big Bang, notably smaller than the Planck scale. Because inflation involves a rapid expansion of space, rather than culminating in a singularity like the original model for the Big Bang, it presents an alternative depiction of the beginning. Instead of time and space gradually emerging from a single state, inflation proposes a rapid expansion leading to the Big Bang. This raises a fundamental question about the actual beginning of the universe, if such a notion even makes sense. Within the framework of the hot Big Bang without inflation, we could trace back and reach a singular state where the universe's size approaches zero in a finite time. However, inflation complicates this scenario. Its exponential growth makes it challenging to trace back to a singularity size, since reaching a state where the universe had zero size would require an infinite amount of time due to the exponential nature of inflation. Adding to the complexity, the observable evidence for inflation, such as quantum fluctuations leaving imprints on our visible universe, corresponds to just the final 10^32 seconds before inflation leads to the hot Big Bang. If we were hoping to delay the start of an earlier grand event, inflation ruins those hopes. There's nothing observable that gives us clues about what, if anything, caused inflation. A fascinating aspect of inflation is called eternal inflation. When exploring how inflation works, almost any model that effectively addresses the issues with the original Big Bang and creates the necessary quantum effects to initiate the universe with imperfections will result in a scenario where, while inflation ends in certain areas like our own, there will be countless more surrounding regions where inflation continues, creating more space that keeps expanding. Essentially, once inflation starts, it wipes out any information about what existed before, and the inflationary state will persist indefinitely into the future. At times, quantum fluctuations akin to those shaping the universe's structure cause certain areas where inflation ceases, resulting in a hot Big Bang. However, these regions are far fewer compared to those where inflation persists indefinitely. Notably, no two separate regions with Big Bangs will ever overlap because the expanding universe drives them apart. Despite its appeal, eternal inflation has limitations. It's eternal only into the future, not into the past. In fact, it's been demonstrated that inflationary spacetime doesn't extend into the past infinitely and must have originated from a prior non-inflationary and possibly singular state. The issue of past time-like incompleteness can't be avoided by considering alternatives like bouncing cosmologies or cyclic cosmologies, as they face similar challenges. However, this doesn't necessarily imply that the universe originated from a singularity. While it could have, it's not a strict necessity. For example, one can envision a space-time resembling the past, where inflation takes place by modeling the universe's expansion rate through a scale factor composed of a growing exponential plus a constant. rather than just a pure growing exponential. In essence, the hot Big Bang, while our most accurate model of the early universe, wasn't its absolute genesis. There's a limit on how far back we can extrapolate the temperature and density of the matter and radiation-filled universe. Prior to the hot Big Bang, there existed a period of cosmic inflation, which initiated and led to the hot Big Bang. During inflation, space was saturated with energy, devoid of matter and radiation, and expanded exponentially. However, inflation couldn't have persisted indefinitely and must have emerged from some pre-existing non-inflationary state. Unfortunately, our knowledge of this earlier state is limited, aside from knowing many things it couldn't have been. We don't live in a universe where matter drifts in empty space. We live in a universe filled with energy fields that interact to form everything we see. When considering the vastness of emptiness, the endless void, and mortality, it's striking how the idea of nothingness can provoke such fear. Did William Shatner, at 90, go on a space journey expecting to find the universe's mysteries, only to realize there was no mystery or grandeur? He encountered only death, witnessing a cold, dark, black void, unlike any darkness on Earth. It was overwhelming and all-encompassing. Yet, in another paradox of nothingness, Shatner wasn't truly observing a void. Rather, he was looking at a vacuum where a lot was happening that he couldn't see. Quantum field theory is one of the most accurate theories in physics, known for predicting the outcomes of many experiments. According to this theory, the universe is not made of matter floating in empty space, but of energy fields that permeate space and interact, creating everything we observe, including ourselves. Some physicists describe these fields as fluid-like, similar to water in a pool, while others compare them to a room filled with varying levels of energy, like a field of distributed heat. These fields are constantly moving due to quantum fluctuations, brief changes in energy similar to ripples in a wave caused by external forces exciting the particles within the field. For example, an electromagnet can cause changes in an electromagnetic field. Even in their lowest state, known as the vacuum state, fields remain active. Pairs of positive and negative particles continuously borrow energy from the vacuum, briefly appear and then disappear, returning the energy. These temporary entities are called virtual particles. When the field is excited or at a higher energy level, it has ripples or waves that produce elementary particles that persist and interact with each other, forming the world we know. The type of particles created depends on the field. Different matter particles are associated with specific types of fermions, such as electrons, up quarks, down quarks, and neutrinos, which are fundamental components of all atoms. These fermions interact through three types of fields: electromagnetism involving photons, the strong nuclear force involving gluons, and the weak nuclear force involving W and Z bosons. According to Cambridge theoretical physicist David Tong, without these force fields, matter particles would drift aimlessly in the universe without interactions or interesting behaviors. Then there's the Higgs field, which Tong compares to molasses spread throughout the universe. The Higgs field gives mass to other particles, stopping them from moving at the speed of light. Tong notes that this comparison is not perfect because it suggests friction, while in reality, different particles interact with the Higgs field in various ways. All fields, including matter and force fields, exist everywhere but interact differently. Some particles in these fields ignore each other while others interact, leading to reactions and complex structures. The collaboration of these fields covers everything we understand and observe, along with much that remains unknown and beyond our perception. Oddly, the creation of matter particles is an exception. For instance, an atom forms when there's enough energy in the quark fields to produce quarks that aren't destroyed by antimatter quarks, though the reason for this is not fully understood. Gluons, which are particles related to the strong force, bind with two up quarks and one down quark to form a proton. Gluons then connect protons with neutrons to create a nucleus. Physicists propose that the visible universe consists of remnants that survive the constant creation and destruction of virtual particles. However, the particles making up dark matter are a different issue. Although the universe is full of virtual particles, it doesn't completely negate the idea of nothingness. First, there's the nothingness before the Big Bang, which we don't yet understand. Additionally, this nothingness, made up of vast fields of quantum energy, seems to produce matter and force, leading to the creation of our world. Physicists are still unsure why some elemental particles persisted after the Big Bang. In his book, A Universe from Nothing, Lawrence Krauss, a theoretical physicist and cosmologist, argued that the evidence holds the answer. The inherently unstable nature of nothingness produces elementary particles. There's also the idea that the entire universe might be a large virtual particle. The vacuum genesis hypothesis proposes that the universe began as a large fluctuation in the nothingness that preceded it. Although this hasn't been proven, it's an intriguing concept. Ultimately, everything, you, me, the whole universe, amounts to a big bunch of nothingness. Even if you can picture an empty universe, this doesn't match reality. Adhering to the laws of physics is enough to dismiss the idea of a truly empty universe. This video, Brian Cox, Something Terrifying Existed Before the Big Bang, explores theories about the state of the universe before the Big Bang. Brian Cox explains complex concepts of physics and cosmology, addressing the possibility of terrifying phenomena that existed before our universe was formed. The video provides fresh and profound insights into the origin and nature of the universe, provoking curiosity and thought about what might have existed before the beginning of time and space. Join us to investigate, analyze, and find out the truth behind each story. Register now to not miss the most interesting content. Thanks for watching.